This is Mario, and Mario is well known for his ability to jump. Actually defines Mario as a character. Mario kills enemies by jumping, and he gets flowers by jumping, and he avoids traps by jumping. He does a lot of stuff by jumping. And this is the path that Mario follows as he jumps. But it's a curved path, and we only know how to do straight paths so far. We have Mario's velocity vector. It's going to look like this. It's going to be a straight line. Here it is, velocity. And we know a new vector for Mario, a gravity vector that we're going to need in order to make Mario fall. And I'm going to call that G. But how do we combine these in order to make this curved path that Mario has to take in order to jump? Well, the answer is that we just cut it up into lots of small pieces, and here they are. We cut this curved path into a bunch of small pieces, and each small piece is actually a straight line, but when you put them together they look like a curved line. And the mechanism that we use to do that is called the game loop. Every game does this. Every single game, from Call of Duty all the way back to Mario, they all use game loops, and I'll show you how they work. Number one, you update things. So you update Mario's position using the gravity and the velocity, and you update the enemy positions, you update the power-ups, you update everything. And then two, draw. You draw things in the new positions. And then lastly, you go back to the beginning. It's a loop. You keep doing this over and over and over and over forever. So then the question is, how long should each one of these individual cuts be? And to answer that, we need a delta t. Delta t is the time that passes between each frame. Each time we do this, that is one frame. Okay? And the delta t is the time that passes between this frame, which I'm going to call t prime, and the last frame, the previous frame, so which is t. So how much time passed between when we're starting this frame and when we started the last frame? That's delta t. So for example, if we're running at 30 frames per second, then delta t is going to be about 1 over 30, or 0.03 repeating. It's a really small number, which means that these are going to be really small steps. If our game is running at 60 frames per second, then our delta t is going to be 1 over 60, or 0.016 repeating. And that's really, really small. I mean, we can fit a lot of those. So we're going to work with delta t's that are really tiny numbers, and we can break this up into little tiny pieces. So let's look at how Mario's position, which I'm going to label M, Mario's current position is M, and how do we update Mario's position every frame in order to get this curvy thing? Well, first, Mario's new position, which is going to be M prime, is going to equal Mario's old position plus delta t, and this triangle is just a delta symbol, that's all it is, times the velocity vector. So this delta t is really small, and it cuts the velocity vector really small, and it moves Mario just a tiny bit. And now we have to update the velocity vector as well. So the new velocity vector, v prime, is going to equal the old velocity vector plus delta t times the gravity vector. So that means every frame the velocity vector is going to be going a little bit more down, just a little bit because of our delta t, but it will be going a little bit more down and down and down and down, and it will give us this nice curve. So good. Let's go to the code and see how it'll all work in C++. Alright, here we go. This is the code, or rather just a small part of the code. We don't have to see all the code right now because there's a lot of stuff with OpenGL that it's not important right now. We'll get to that later. But we have an update function, which I haven't stubbed out yet. We're going to put stuff here. And we have a main function. First thing on our main function is I just set a few default parameters for Mario. I just set his default position and his velocity and his gravity. So we'll have that later. And then I set the previous time. These are just defaults. We're going to change them later anyway, so I'm really just declaring the variables so that I can use them. Okay, let's start with our main loop, our game loop. And we can do that with a while true. If you remember from your programming class, while true will loop whenever what is in the parentheses is true. And since I just put true in there, it means it will always loop. Great. So the first thing we do on our loop is let's set delta t. And in order to do that, we need the current time and the previous time. So I'm going to start with setting the previous time. The previous time is whatever the current time was last frame. This current time variable will be hanging around from last frame, and I'll just borrow it and set it to the previous time, and then I'll set the current time to get current time, which is a function that I set up elsewhere in the code that does exactly what it sounds like. It gets the current time. So now hopefully FL current time will be a little bit larger than FL previous time. And if you're wondering what these FLs are, they're just a prefix that I voluntarily put at the beginning of some of my variables. It's called Hungarian notation, and it helps me keep straight what variable is what. So I can tell this is a float because it says FL at the beginning of it. And now we can calculate our delta t. And that is, just like the equation says on the right, the current time minus the previous time. Done. Now one little trick I like to use with delta t, it's actually pretty important. If delta t grows greater than a certain value, I like to use 0.15, then we have to lock it down because it's supposed to be a very small number, if you remember, because we do many little slices at a time. So if it grows too large, then it's not useful for us. So if the game freezes, then when you come back, everything is going to have flown all over the place because dt gets too big. So we're going to lock it down. Now going back to our game loop, we need an update, and I have our update function up here. It takes a delta t, so there's our delta t, and then draw. I've defined our draw function elsewhere. Don't worry about what's inside it for now, just it draws Mario where we position him. And that's it. That's our game loop. So now let's go up to the draw function and fill that in. Two things we have to do. First, let's set Mario's position. Here's the formula. Mario.new position. We're going to set it to Mario's old position plus Mario's velocity times delta t. And then Mario's new velocity equals Mario's old velocity plus the Mario's gravity times delta t. Now what's this keep Mario within borders thing? Well, that's just so that because he's going to be jumping all over the place, we're just going to keep him inside of the window borders, and you'll see what I mean as soon as I press F5. And there you go. Mario's jumping around. So now you too can have velocities and jumping and gravity in your game using the game loop. And we're going to use this, we're going to expand upon this game loop in later videos. There's a lot more stuff you can put in it, like taking user input, doing networking, which we're not going to get to until a lot later, but networking and physics and all this other stuff. So I'll see you in later videos.